Hello friends, this is Isro question paper heat transfer part 7. This is 2015 paper. Question is, a coolant fluid at 30 degrees Celsius flows over a heated flat plate maintained at a constant temperature of 100 degrees Celsius. The boundary layer temperature distribution at a given location on the plate may be approximated as T equal to 30 plus 70 into e to the power minus y, where y is the distance normal to the plate in meters and T is in degrees Celsius. If thermal conductivity of the fluid is 1.0 watt per meter Kelvin, then the local convective heat transfer coefficient in watt per meter square Kelvin at that location will be how much? Here our formula is at y equal to 0 is HAS Ts minus T infinity, or here they asked convective heat transfer coefficient local H equal to minus K AA cancel minus K dt by dy at y equal to 0 divided by Ts minus T infinity, surface temperature divided by fluid temperature, outside fluid temperature. Here data are Ts is 30 degrees Celsius and flat plate, this is T infinity 30 degrees Celsius, surface temperature is 100 degrees Celsius, and T equation given 70 e to the power minus y, K also given 1.0 watt per meter Kelvin. So we use these things. First dt by dy at y equal to 0 we will calculate. Dt by dy, T is 30 plus 70 into e to the power minus y. So 0 plus minus 70 into e to the power minus y at y equal to 0. At y equal to 0, e to the power 0 is 1. So it's minus 70. So if we put k is 1, minus 1 into minus 70 by Ts minus T infinity, 100 minus 30 is 70. So it's 70 by 70, 1. 1 is our answer, 1 watt per meter square Kelvin. Local convective heat transfer coefficient, B is our answer. Next, a furnace wall is constructed as shown in the figure. The interface temperature T1 will be how much? This one T1, interface temperature. Here this temperature they asked. So data given are, take this one 1, this side 2. So here this one T1 na? Interface temperature is T1, so this side you said I and O. Ti inside is 1000 degrees Celsius and K1, this plate 1, this plate 2. K1 is 3 watt per meter Kelvin. L1 thickness is 0.3 meter. This side T outside is 120 degrees Celsius. This is T infinity. That is not required. K2 is 0.3 watt per meter Kelvin. L2 is 0.3 meter. Q by A, heat transfer rate is same everywhere. So for plate 1 and plate 2, so we'll take K1 delta T by L1 equal to K2 delta T by L2. So K1 given 3, delta is 1000 minus interface temperature divided by 0.3 meter. Here K2 is 0.3 into T1 minus 120 degrees Celsius divided by 0.3. 0.3 cancel. And here 0.33, here 10. So it's 10 to the power 4 minus 10 T1 equal to T1 minus 120. So 11 T1 equal to 10120. So interface temperature T1 is 10120 by 11. If we calculate 11 into 9, then 2, then 0 degrees Celsius. From option, it's C is the answer, 920 degrees Celsius. Next question. Your finger sticks to an ice tray just taken from the refrigerator. Which factor has more effect on this phenomenon? A. The inside temperature of the freezer. B. Humidity of the air. C. The heat capacity of both your finger and the tray. D. The thermal conductivity of the tray. D is our answer. Next question. A 10 kg solid at 100 degrees Celsius with a specific heat of 0.8 kJ per kg degree Celsius is immersed in 40 kg of 20 degrees Celsius liquid with a specific heat of 4 kJ per kg degree Celsius. Estimate the temperature after a long time if the container is insulated. Specific heat of water is 4.18 kJ per kg. Here the data given are M1 is 10 kg, temperature, specific heat 0.8 kJ per kg degree Celsius, immersed in 40 kg M2, T2 is 20 degrees Celsius, specific heat Cp2 is 4.0 kJ per kg degree Celsius. Estimate the temperature. TF they asked. So heat loss by hot fluid is heat gain by cold fluid. If you use this one, M1 Cp1 T1 minus TF is M2 Cp2 TF minus T2. So put the values. 10 into Cp1 is 0.8 into T1 is 100 minus TF Here M2 is 40, Cp2 is 4 into Tf minus T2 is 20. So we will get is 4. Here you take it as 8 by 10. Then 4 8 is 2. Here it's 5. So we will get 100 minus Tf equal to 25 into 4 is 20. 20 direct we can write 20 Tf minus 20 into 20 is 400. So 21 Tf is 500. So final temperature Tf is 500 divided by 21. So it will come around 21 first 2, then 2 8, 80, then 3, 63, then 17, 170 by 21, around 8, 23.8 degrees Celsius. So from option it's nearly 24 degrees Celsius. D is our answer. For a current wire of 20 mm diameter exposed to air, H equal to 20 watt per meter square Kelvin, maximum heat dissipation occurs when thickness of insulation is K equal to 0.5 watt per meter Kelvin. Its wire means cylinder. Already discussed at critical radius, Q is maximum. Q and R. Here Q max at critical radius. RC. So for cylindrical RC is K by H. So K is 0.5 by H is 20. 0.5 by 20. Take it as 5 by 10. 1 by 40. This is in meter. So multiply 1000. You will get 40 into 25 is 1000. 25 mm. But in this question they ask critical thickness of insulation. This is critical radius. This is critical radius. But they ask critical thickness. This is very, very important for all exams. Critical thickness and critical radius. Critical thickness is here we will get if wire is like this. This is RI. This is RO. Critical thickness is this one. Critical thickness TC is RO minus RI. So in this case we got RO 25 minus diameter given 20 mm. So divided by 2 is 10 mm. 15 mm is our answer from option. This is none of the above. D is our answer, but in Isro official answer given as B. But it is critical radius. Sometimes they are giving wrong answer also. That same type question asked, but that time they corrected that one. Here In Isro official answer, B was the answer, but answer coming as D. Next question also same question, little bit different. Here they asked optimum thickness of enamel paint, same. RC will get K by H. K is 0.1 divided by heat transfer coefficient is 100, so it's 1 by 10, 0.1 or 1 by 10, it's 1 by 1000, so it's in meter, it's mm in 1 mm. So this is our wire, this is thickness of enamel. So this is R inside, this is R outside. R outside, for optimum thickness we got RC equal to R outside, we got 1 mm. Inside 1 mm diameter means 0.5 mm. So critical thickness is RO minus RI. It's 1 minus 0.5, it's 0.5 mm. But this time they gave the correct answer. B is the answer. Next, a steel ball of mass 1 kg and specific heat 0.4 kilojoule per kg. It is at a temperature of 60 degrees Celsius. It is dropped into 1 kg of water at 20 degrees Celsius. The final steady state temperature of water is how much? M1 1 kg, Cp1 is 0.4 kilojoule per kg, T1 is 60 degrees Celsius, M2 is same 1 kg, T2 is 20 degrees Celsius, Cp of water is 4.2 kilojoule per kg. So heat loss by hot fluid is equal to heat gain by cold fluid. M1 Cp1 into T1 minus final temperature equal to M2, this is Cp2 into Tf minus T2. So 1 into Cp1 is 0.4 into 60 minus Tf, M2 also 1 kg, Cp2 is 4.2 to Tf we have to calculate, this is 20. Here 21, so it's 120 minus 2 Tf equal to 21 Tf minus 20 into 21, it's 420. So 23 Tf equal to 420 plus 120, it will come 540. Tf equal to 540 divided by 23. 23 into 2 is 46, 880 into 3. 23 into 3 is 69, 11, then 110 by 23. 23 into 4. So it will come nearly 23.4 degrees Celsius. So A is our answer. In a pulverized fuel-fired large power boiler, the heat transfer from the burning fuel to the walls of the furnace is, it's predominantly by radiation. All three modes they are doing, but predominantly by radiation. First they give, in official A they gave answer as C, but later they corrected as D. D is our answer. All three modes are possible, but predominant is radiation mode. This is very important for all other examination also. Next, three metals walls of the same cross-sectional area having thermal conductivities in the ratio of 1:4 transfer heat at the rate of 6000 kJ per hour for the same wall thickness. The temperature drops will be in the ratio of how much? K1 into K2 into K3, 1 into 2 into 4, and Q 6000 kJ per hour. Same wall thickness. So L1 equal to L2 equal to L3. Here we know Q equal to Ka T by dl. So K is inversely proportional to delta T, or delta T is inversely proportional to K. So directly we can do, that's 1 by K1 into 1 by K2 into 1 by K3. So it will come 1 by 1 is 1, is 2, 1 by 2 into 1 by 4. B is our answer. Otherwise, different method also you can use, little bit lengthy. K1 delta T1 equal to K2 delta T2 equal to K3 delta T3, as Q by A is same. Here K1 by K2 is 1 by 2, K2 by K3 is 2 by 4. From here K2 is 2K1, from here K2 is K3 by 2. So here delta T1 by delta T2 is K2 by K1, and delta T2 by delta T3 is K3 by K2. So here delta T1 by delta T2 is 2K1 by K1, it's 2. Here delta T2 by delta T3 is 2K2 by K2. K2 cancel. Delta T2 is 2 delta T3. So here delta T1 is 2 delta T2. Then 2 delta T2 delta T3 equal to 2 delta 2 into delta 2 to, this is little bit lengthy, but you can get your answer. This one will get 2 into 1 into 1 by 2. So divide 2, we'll get 1 into 1 by 2, 1 by 4. B is answer. Same answer we get. Choice is yours, which one you can take. A flat plate of length 1 meter and width 50 cm is placed in an air stream at 30 degrees Celsius, blowing parallel to it. The convective heat transfer coefficient is 30 watt per meter square Kelvin. The heat transfer if the plate is maintained at a temperature of 400 degrees Celsius is how much? Here data given are surface area is 1 into 0.5 is 0.5 meter square. Then air stream temperature is 30 degrees Celsius and surface temperature Ts is 400 degrees Celsius. H also given 30 watt per meter square Kelvin. We know Newton's law of cooling. Ts minus T infinity. Put the value. H is 30, A is 0.5 into 400 minus 30. So we'll get this is 30 into 1 by 2 into it's 370. So it's 15. 15 into 37 you multiply. It will come 555. Add 10, it's in watt. But in our option it's in kilowatt. It will come 5.5 kilowatt. From option A is the answer. It is required to insulate a kitchen oven with cork board K equal to thermal conductivity given 0.043 watt per meter Kelvin, so that the heat losses from the oven does not exceed 400 watt per meter square. Q by A also given. When the inner surface of the oven is at 225 degrees Celsius and the outer surface of the oven is at 40 degrees Celsius, the thickness of insulation required is nearly how much? It's like this. This thickness, there's L. One side temperature is here, other side is 40 degrees Celsius. K is 0.043 watt per meter Kelvin. Q by A also given 400 watt per. It should not exceed this one. So for your law, Q by A equal to K dt by dl. We have to calculate dl. Delta L is K delta T into A by Q, or here Q by A. If you take this one, 0.43 into 225 minus 40, it will come 185 divided by Q by A. It's 400. So 0.043 we can write 43 by 1000. If you calculate this one, in this question it is answers are in cm, so we will multiply 100. Then this is 4, 185 by 4 is 4 into 4 then 6.2. Here 46.2 into 43. If we multiply 6, 8, 1, 8, 4, I'll get 6, 6, 8, then 9, 1, 1.1986.6. So we'll get 1986.6 by 1000. 1986.6 by 1000. This is in cm. So come 1.9 cm, nearly 2 cm. From option B is the answer. A radiator in a domestic heating system operates at a surface temperature of 55 degrees Celsius. Assuming the radiator behaves as a black body, the rate at which it emits the radiant heat per unit area is assumed as. Stefan Boltzmann constant also given. So we already discussed Q by A sigma T2 for black body, so epsilon is 1. Here we will get Q by A sigma is 5.67 divided by 10 to the power 8 into 55 plus 273 into 328 to the power 4. So you can take it as 5.67 into 10 to the power 8 into 300 to the power 4. So if we calculate 5.67 10 to the power 10 to the power 4, 10 to the power 8, here 300 to the power 4, all zeros are cancelled, then 3 to the power 4 is 81. So it's 328, so more than 81 you have to calculate, so you take it as 100. Approximate method we have to use, so it's 5670 watt per meter square. In kilowatt it's 5.67 kilowatt per meter square. It's 567. Here it's 0.567 watt kilowatt per meter square. 0.567. It's nearly. This is not possible. This is also not possible. 0.567. It's nearly more than this one. So nearly A is our answer. Without calculator it is little bit difficult. So our option A is our answer. A gray body is defined such that A. Monochromatic emissivity of the body is independent of temperature. B. Monochromatic emissivity of the body is dependent on temperature. Monochromatic emissivity of the body is independent of wavelength. C is our answer. It's independent of wavelength. Next, critical thickness of insulation yields. This one already discussed. Q by R. Here Q maximum. Here critical thickness. Maximum heat transfer rate from a pipe. C is our answer. A beaker filled with hot water in a room cools from 70 degrees Celsius to 65 degrees Celsius in T1 minutes, 65 degrees Celsius to 60 degrees Celsius in T2 minutes, and from 60 degrees Celsius to 55 degrees Celsius in T2 minutes. Then T1, T2, T3 relation we have to calculate. 70 to 65 in T1 minutes, then 65 to 60 in T2 minute, 60 to 55 degrees Celsius in T3 minute. Delta T is same, 5 degrees Celsius. So here T3 is greater than T2 is greater than T1. From option A is not possible, B also not possible, D also not possible. So C same, T1 is less than T3. C is our answer. If the temperature of the sun is double, the rate of energy received on Earth will be increased by a factor of dash. We know E equal to sigma to Ts to the power 4. Temperature is increasing. E1 is sigma A Ts to the power 4. E2 temperature, only temperature is increasing, other factors are same. So it's 2 Ts to the power 4. So it's 2 to the power 4 is 16 sigma A Ts to the power 4. It's 16 into E1, increased by a factor of 16. The transmission of heat by molecular collision is called as A convection, B conduction, C radiation, D ionization. Ionization not possible. B is our answer. Transmission of heat by molecular collision. If two ends of rods of length L and radius are made of same material are kept at the same temperature difference, which of the following rods conduct most heat per unit time? Already discussed. K delta T by 4 rod. Q is proportional to A by L. A in terms of R square, it's rod, so proportional to R square by L. Area is pi R square, so it's proportional to R square divided by L. So Q proportional to R square by L. From option you check all options. For A it's R square, 1 centimeter square is 1 by L is it's 50. B Q is 0.5 is 1 by 2 square is 1 by 4 into 1 by 2, it's 1 by 8. C Q is R square, 2 square is 4, then by L is 100, it's 1 by 25. D Q is R square is 1, L by 1 by 3. So Q is maximum in case of D, 1 by 3. D is our answer. Thank you friends for watching my video. Thank you. This is the end of heat transfer Isro question paper from 2006 to 2016. Thank you.